Students, welcome back to the part 2 of lecture number 38. So, we have been talking about different kind of databases, and I told you in material science there are 3 types of databases available traditionally: material behavior, which is giving you mechanical, physical, functional properties, and then you have also databases from thermochemistry or thermodynamic data sets, which can give you specific heat information and enthalpy or calorimetric informations. And then you have a crystallographic data set which can provide you crystal structure, lattice parameters, atomic location, etc., etc. Okay. So, these 3 databases are the ones which are available, which you can access, obviously by not free of cost, by paying some money, but this are available and this has been developed over the time scale. So, let us now discuss how we can go about it. I will go back to Michael Ashby. It is not because I like him, but it is because whatever he has done is phenomenal. When you talk about materials behavior, you have to discuss different types of materials: metallics, ceramic, polymeric, glasses, elastomers, and combining it, this can give you hybrids or composites, right. So, that means it is a massive number of materials. So, collecting data or creating a database of different properties of different material is not a very easy job, it is rather a very difficult job. So, we always undermine the material world. Material world is very big, and when you talk about different alloys, God knows, maybe there are 10,000 alloys possible, out of which we are using probably 2,000 alloys in our real life. Steel itself has different types. Then you have ceramics and polymers, composites, glasses, elastomers, right. The specs which I am wearing has glasses as well as the frame is a metallic, right. So, you can see that there are different combinations of materials are used. So, now the question is, if that is the case, how do you understand the behavior of these materials? Well, obviously, Michael Ashby proposed material selection charts, and that is the way better to represent data, and this is visualization. So, it will allow us visualization of the properties, and we always like to see things in front of our eyes. We do not want to see things in our mind, right. That is why visualization of these material data are very important, and it can show different types of materials, lots of different type of material. We can actually even drill down to specifics, and we can always find out balanced set of properties. This is actually rough, ideal for the first rough cut. Now, you can say that, but they are good for making selections. As you know, the Michael Ashby's work is so good in those days, and this is considered one of the systematic efforts to address the challenge that we face when you talk about data or developing data sets. And this is done by Michael Ashby and co-workers long back, 20 years, 25 years ago. They have shown that by merging phenomenological relationships on the established properties with discrete data on specific materials characteristics, one can begin to develop patterns of classifications of the materials. The hidden patterns can be found out. So, I remember when I was a student, I have done this course on material selections in mechanical design, and that is how I was exposed to this concept called this material selection charts, and then I was amazed how it was thought about it, how data are obtained from different sets or different parts of the world, and the selection charts are made. So, the visualization provides you a lot of idea about how to balance the properties, how to make selections. This is something which you must have heard about it, right. So, what are different properties we talk about it? Many. Mechanical means strength, modulus, ductility, toughness. Physical means density, melting temperature. Electrical means conductivity, resistivity, many more. We can also talk about aesthetic like appearance, texture, color, processability. If the material is not ductile, you cannot process it by deformation processing, moldability. We all talked about all these things at the beginning of this course. And last but not the least, cost is also a factor when you talk about material properties, right. Because you are designing or discovering a new material for actual applications, the cost is a factor. So, where from you get the data? There are 4 sources of these material properties. First is a textbook. You can also have data books, manufacturer literature and internet sites. That is very important. These are the different sources of data, you can get it, right. So, then let us discuss one by one out of these. Textbooks, they are good for general information. Some of the textbook will provide you tables of properties, like the textbook on mechanical behavior of materials by George D. Dieter will provide you tables of some properties, right. But you know, they are not good for detailed specification and properties, they may give you some ranges of properties. So, therefore, textbooks are good for general information. Data books, this is one of the quickest source of detailed information. To give an idea, Smithell Metals reference book, you know, this was edited by W. F. Gell and T. C. Totmeyer long back. Now we can get 8th edition also in 2022 or something. So, this is one of the quickest sources of detailed information. I remember when I was a student who used to use this Smithell handbook very often to find different data or properties of materials, and they usually contain grades and specification as well as properties. They are small but perfectly formed pocket books, that is why they are easy to navigate. So, this you understand, whatever we are talking a new subject of informatics, people have or our forefathers have discussed about data books. We always used to think about it, but nowadays none of us maintain data book so nicely. This is one of the problem of using mobile phones and computers. Then the third one, textbook, data books. Third one is manufacturers literature. They are not very useful because they are variable in quality and usefulness. Manufacturers will advertise their own products, so they will focus on certain things, often only cover their products, usually do not compare materials. So, therefore, can be biased, but you know, they can be good for final selection before ordering, that is what it is. Otherwise, they are not very useful, please understand that. They are not very useful in the sense that they are kind of, you know, advertised, that is why. Then come the internet, which we all are so much, you know, glued to every day and night. Internet can be a real minefield, lots of poorly presented information, you do not know which one to take, which one to filter out. Google searches brings up lot of rubbish. Yes, that is not my sentence, that is sentence of many of these scholars also. Many times you will see the searches will not provide you authentic informations, you need to dig deeper to get authentic informations, and in many cases it is hard to find even technical informations. So, therefore, best is to use non-commercial sites, and Google will take you those non-commercial sites at the end. After you probably some 3-4 pages you will find those non-commercial sites, but we always like to see first 10 hits, first 15 hits in Google search, right. That is why internet is not a good way to get information. Now, look at what Michael Ashby's book can provide. Well, Michael Ashby has given this material behavior, mechanical, physical, functional property in terms of charts, and that is his novel idea, because charts I am going to discuss about that in quite a extensive manner in the next 10 minutes or 5 minutes or so, 5-10 minutes. This is the chart between Young modulus of density of different materials, and if you look at, he has used classification algorithm, right. He has classified the different materials like foams, woods and wood products, polymers, rubbers, porous ceramics, metals and alloys, ceramics, composites. So, you can actually have a nice correlation of these properties, different materials having the Young modulus and different densities. Now, if you look at carefully here, that is what subclasses are given. Look at the foam, these are actually rigid foams, this is cork, flexible polymer. Within the foams, subcategories are given. Similarly, within polymers, even different subcategories are given, like silicon elastomers, polyurethanes, many others. So, he actually methodically collected data, authentic data from different sources and classified them, put in terms of charts. So, these charts are actually source of information. One can actually gather information, material property information from these charts very easily. Nowadays, you can get in terms of information CD or so, or CD-ROM, or maybe in pen drive, you can get this data and use it. So, therefore, creation of data looks like is very, very important for material informatics, and this is authentic source of the material selection charts, authentic source of the data. So, please keep in mind that once if you get time, go through this book by Michael Ashby, material selection in mechanical design. Another chart called strength density chart. Okay, look at it. Density is basically in this unit meter cube, strength on the right on the y axis. Ceramics are the strongest one, that is why they are at the highest. Composites are mixed of ceramics, metals or polymers, that is why in between them. Then you have woods, foams, all these things. On the right I am showing you best combination of data. Now, you can also see the different lines are drawn. These are basically correlation analysis, which we will do in the next lecture, how to do a correlation analysis of these kind of data sets. And these correlation analysis are considered as a guidelines for like minimum mass designs. So, as you understand, when you talk about design, you are having a set of properties given to you, and then you have to select a material, or you have to design a material, or you have to make a new material or discover a new material, whatever. That is only possible when you have data. So, these actually charts are providing you a lot of data, and they are not only important in terms of providing you correlations, but also in providing you classifications. So, classifications of the different kinds of models, we talked about it when you discuss machine learning, remember at the beginning, and of machine learning classification is one of the unsupervised learning techniques. But here you look at it, he has classified this. If you look at this chart, is much better. He has classified this woods, foams, elastomers, polymers, metals, composites, ceramics very nicely. And this is a set of materials, engineering materials we use in day to day life. And if I want to have a strong material which is low density, okay, that is what I use for space applications. So, I should be searching density between 1 and 2 or 1 and 3, right. I should not search densities of 10 or 15. So, therefore, then I have a limited choice window, and then if I want to have a high strength like more than 100 GPS, then I have only set of metals, ceramics, composites only. That is what is the main idea of these charts, that will allow you to select materials based on this set of properties. So, let me move ahead on this. This is on functional property like thermal conductivity versus electrical resistivity. As you can see here, thermal conductivity of metals are normally very high, as the electrical resistivity is also very low, we know that. So, they come here as a one elliptical area. Then you can also have ceramics and composites, polymers, elastomers. So, polymer elastomers, they are normally used as a insulators, some of the ceramics also. So, they have very high resistivity 10 to the power 20, 10 to the power 15 to 20, right. But composites can be having combinations of high, high thermal conductivity, not high, but okay, medium type thermal conductivity with reasonably good resistivity. This is what is subclasses. You can see here within the metals, Michael Ashby and his team is showing copper alloys has the highest electrical thermal conductivity. After the aluminum, zinc, tungsten, magnesium, steels, titanium alloys has a much lower thermal conductivity. That is why for any thermal application we do not use titanium alloys, we use mostly copper aluminum alloys, although titanium alloys may have higher melting temperatures. But copper is probably the best one because it has higher melting temperature as well as higher thermal conductivity, and it can be used for a application where you also need to take care of the electrical conductivity. So, that is why copper alloys is the best candidate for electrical thermal applications. You may say that we know, yes, we know about it, but it also talks about it if you want to find out some alternatives of copper, what all you can choose. Next alternative should be aluminum. That is what is done in air conditioners. If you have seen air conditioners, inside in the air conditioner kind of pipes they use are basically made of either copper or aluminum. Similarly, wires can be either copper or aluminum, electrical wires. So, these are all experience based, but the theory or the data science also provides a strong confidence on that. So, that is the one which Michael Ashby's charts can provide. So, I am just showing you a tip of the iceberg. his book is going to provide you details of that, and these charts are made after a lot of struggle in getting the data from different parts of the world. That took a lot of time probably for the team to do that. Now, let us go to the next set of data, right, what is called thermodynamic data sets. Thermodynamics data set means we know that important function in thermodynamics if he gives me energy, which is nothing but H minus Ts. Enthalpy, this is enthalpy, T is the temperature, and S is entropy. So, we can always write down this is Cp dt, and this one is Cp by dt, right. So, what you need to know is the Cp, heat capacity. Also, you need to know latent heat, that is what calorimetric data. This is called calorimetric data. So, most of the thermodynamic data sets will have that, and then you can build free energy data sets, free energy things also already, right. So, this is taken from Thermocal, and Thermocal provides you a lot of databases. I am just listed few, but the actual Thermocal products will provide you many databases, steel iron databases, nickel alloys, aluminum, magnesium, copper based alloys, titanium, molten salt, refractory alloys, lumen metals like platinum, palladium, gold, silver, silicon based alloys, semiconductors, oxides, slags, high entropy alloys, Holder alloys, cemented carbides, zirconium alloys, high temperature materials, ultra high temperature materials, permanent magnets, minerals, general alloys and substances, nuclear materials. To list few, there are many more actually. So, these databases are available, you can buy them actually. You cannot use it free of cost, because these are expensive, because that is how they make business. So, as you know, with these databases you can use a CalFAD approach to design or get phase diagram informations, right. So, what do you do that? In CalFAD approach you have thermodynamic functions G, H, S, P, you can see that thermodynamic functions, and then you can actually have generate this thermodynamic function from the stored databases. You can actually adjust various pre-parameters of the thermodynamic functions, and using different models will have adjustable parameters, and this adjustable parameters, this model actually can be obtained from quantum mechanics, experiments or estimates also. We have talked about it, these aspects that requires some kind of optimization, and once you optimize the thermodynamic properties, then you can use for your calculations. So, remember, using only thermodynamic data may not allow you to get good information from your systems. Many times you need to do a lot of optimizations, and that is something which we talked about it when you discuss about different length scale issues. So, finally, you get phase diagrams, phase equilibrium informations, and you can make a graphical representations of that. That we material scientists know very well, that graphical representations of these phase equilibrium phase diagram informations are there. So, CalFAD approach does that. As you know, free energy is a function of these plus this excess free energy, that is why you have a lot of free parameters. For these first two terms you cannot do much, only third term you can do a lot of adjustments. So, and then you can get a assess the data, optimize it to get a good free energy estimates, and this once you get that, then you can use this free energy information for thermal calculations or calculations for phase diagrams. You can do diffusion induced phase transformation calculations, or you can do even both. That is what done is Prisma nowadays. These are all built in softwares, by the way, by the Thermocal, and you can actually get these softwares when you buy the databases from them. So, remember, other than Thermocal, you also have Pandat, which is also a new company, not new, they are also selling databases and all these softwares to do that. So, now the third one is called crystallographic databases, and this is the comprehensive literature coverage from 128,000 original published. This is taken directly from Pearson Crystallographic homepage. I am just copied from there. I do not want to distort the information what they have given it. So, it can provide comprehensive literature, world literature over 1,28,000 original publications, and it can provide you phase informations like crystal structure, chemical structure systems, unique formula. It can also provide you various kind of crystallographic data like atomic coordinates, crystal structures, their lattice parameters, Wyckoff notations, and many more. You can go through this literature, and nowadays we can get this, many of us has these data sets available in our libraries. So, therefore, crystallographic data sets actually are very unique, and they provide a lot of insights into the different kind of crystal structures which forms, and these data sets actually every time are updated because of new discoveries and new concepts which are coming up all the time, always. So, this is the home page of the Crystallimpact.com, and it is by Pierre Villers and Karin Senzuel, they are editors. You can buy even these hard copies, and they provide 3,95,000, that means 3.95 lakhs entries, almost close to 400,000 entries, and this is released recently 2023-24. So, you can imagine it is a huge database, one can use this database to do calculations. Crystallographer do that. And this is one such snapshot directly from this home page or their product catalogs. You can see a complex chemistry. Can you see that? This complex chemistry, they are analyzing it. So, you can analyze all kinds of chemistry, look at crystal structure, atomic location, everything information is possible, whatever you can get it. Well, that is about the available databases. So, can you create new databases? Answer is yes. That is why I taught you NLP, the natural language processing. So, students, you have learned a lot of techniques of databases, different types of databases. You can also create your own databases, right, by using what is known as a technique called NLP. So, that is what is called use of NLP in database creation. So, NLP can be used to create new databases. Sometimes you can create your own database and use it, right, that is what is called NLP. And as you know, machine learning is a versatile tool. It can do all kinds of things. It can do image recognition, it can do email spam, it can also do online fraud detections. Similarly, it can also do speech recognitions or many other things, which is including the natural language processing, what is called NLP. It makes your task very easy, by the way. So, how it is making easy? Well, if you want to do experiments and generate data and use it analysis, that will be time consuming, that will take a lot of resources. On the other hand, if you can generate data using different kinds of, you can develop a model and then you can predict it, then it will be very fast, time efficient, resource efficient, and that is the need of the hour, because we want to accelerate the design and discovery of new materials, and that is possible once you have machine learning based models possible. But underlying fact of having machine learning based model is data, and without data you cannot do modeling, right. That is why data to database, what we have talked about it in the earlier part of this lecture. So, how can you generate data? So, we call it design to device. Okay, we can take scientific literature, what are available in the globe in terms of publication, in terms of reports, in terms of books or many other things, that is part of scientific literature. Extract the information and compile it. Once you extract information, you have to do data preprocessing also, because there may be some missing data, wrong data, some outliers. Then you compile it. Once you compile it, you collect data sets, right. From that you can predict, you can validate whatever you want to do. So, these two, from the generation extraction of the data from scientific literature to extraction to compile, that is can be done by NLP, right. That can allow you to create new databases. So, what is that? You can have articles, scientific articles, you can have papers, you can retrieve information from that. Then you can also have databases, as you have talked about it. So, from there also you can find out relationship extractions, and finally, you can do data preprocessing and technical evaluations, right. That is what is done. So, how this extraction of data are done? That is what is done by NLP, right. So, NLP uses different phases. You can use morphological processing, syntactic analysis, semantic analysis, discourse integration and pragmatic analysis. If you go back to my earlier lecture on NLP, we can do all these kinds of things, but most important thing what you can do is what is called a name entity tagging. Because if you want to create database, let us say you want to create database on mechanical properties of steel. So, that is your tag, and we can, this entity identify, allows you to identify, categorize and tag name entities in data. So, if you create this name entity, it will go and search that in the literature, identify it, extract it and classify it. So, purpose of NNTB is to automatically extract the structural informations from the unstructured text, and that allows machines to understand, categorize entities in a meaningful manner for various applications, right. You can create in terms of graphs, you can create in terms of plots, or that is the idea actually. And how does it work? It provides you NEP tools, NER tools, okay, or rather named entity tagging tools like name, country, company or whatever for any person you ask, and it creates these tag words or phrases basically that will be then searched in the literature, and once these tags are found you can extract information. That is something which is widely done. So, there are different kinds of named entity tagging, like let us say material word embedding, you can have this kind of software, word to VC, fast text, Elmo, okay. Or annotated material text, it can be plain text synthesis of paragraphs or materials, like text mined query or nil temperature, it can mine it, this is found from ELISA, okay. So, there are many ways actually one can do that. So, once you do that, you can develop a query search from the downloadable papers, and then you can create what is known as a database, and that database can be used for all kinds of things, analysis like you can do classification, you can do recognitions. I do not want to go up details of that. So, this is one such examples. So, you can have corpus of 2.5 million abstracts, 4 million abstracts, and using this NER you can actually pick this poly word from polymers and create lot of materials or obtain lot of data. That is what I was trying to see. This is one example. So, one can take many more examples and show that, but that is not the purpose of this lecture. What I am trying to say is that if you want to create your own databases, you can use any R and technique and generate databases. So, let me stop it here. Thank you, and we will get back to lecture number 39 with more analysis on data mining. That is what is the next part of the lecture, data mining and data analytics, where we talk about it, how data mining can be used to predict the different kinds of trends, and along with we will talk about statistical correlations, what is known as data analytics. Thank you.